Yay, polar thingies, polar thingies. Okay, so we've traditionally been operating in Cartesian land, and in Cartesian land we label points x, y. X is the horizontal position, y is the vertical position. We have also looked at parametric equations which travel along a Cartesian path, or sometimes we can find it easily, sometimes it's impossible to find. But the idea is we can model motion with parametric equations. There are other shapes. There are other relations. There are other relations that are best modeled by a different coordinate system, and that coordinate system is called polar. What two pieces of information do you need to describe any point on the plane in polar land? What's one piece of information you need?
Radius.
What is radius? What do you mean?
Distance from
the distance from the origin. So you need r. You need the distance from the origin. That's correct. And then you also need the what? Which is the what? Angle from what? Give me something. From the positive axis going in the... So r is the distance the point is from the origin, and theta is the angle measure going in the counterclockwise direction from the positive x-axis. Do you understand how those are complete sentences? Or even more complete? I think there's a verb in there. But the idea is you need r and you need theta. You need r and you need theta. So for example, q. Could someone tell me what the coordinate is in polar form of q? What's the radius? 5. And what's the angle measure? 0. So that's actually kind of cool. That's the same coordinate in Cartesian and in polar form. What about u here? If I told you that u in Cartesian land was 3, 4, can you tell me what the coordinate is? Can you tell me what the r value is? What's the r value? 5. It is 5 because it's the square root of 3 squared plus 4 squared. It's the magnitude. What about the angle measure? 3, 4, 5 triangles. You might remember what the angle measure is because it is relatively common, but is that a nice trig value? No. Inverse. You want to do inverse sine? I like inverse tangent better, yeah. Tan inverse of what?
4/3.
Yes, 4/3. You could write it like that, absolutely. Now that's not something I expect you to know off the top of your head. I think it's like 57.5 degrees, I think. I think it is. Is it 53?
53 and 47.
It might 53 and 47. Yeah. So the base of this. So this is. Oh, is it 53 and 40? Yeah. The thing is, 3, 4, 5 is it's the smallest Pythagorean triple. So therefore it comes up. What about p here? P is going to be 3, 6. So what's that one going to be? What's the magnitude going to be? The square root of 9 plus 3. 40 what? 5, right? 36 plus 9. And then tan inverse of what? 2. Good job. Yeah, exactly. Now, for some of these, you really need a calculator if you were going to come up with a degree measure. Yeah, absolutely, absolutely. But the idea is you can describe any point in 2 space like this. But what's the point? Why do we need another method? What's the point of this? I mentioned it briefly, but what's the point? Why? Yeah.
Because some things are easier to describe in a polar context.
Some things are really, really easy. Can someone give me the easiest thing you know of that is the biggest payoff? Yeah.
A circle.
A circle. Like a circle of radius 1 around the origin. What's the equation for that?
R equals 1.
Done. That's a circle. I don't know. Circle of radius 1 around the origin.
Is it possible to have the circle not centered around the origin?
Yeah, absolutely. But it's going to modify things a little bit because the r value is not always constant, because the r value is always the distance to the origin. If you move the circle, the r value is no longer the radius of the circle. The r value is going to be something else and a little more complicated. We'll do that, absolutely. But the idea is certain shapes are much easier to model in polar land. Much easier to model. So what you generally see, if you want to look at all the math here, x equals r cosine theta and y equals r sine theta. Why are these two statements important? What do those two statements allow you to do? It's a bridge between the two. So how do you see that? How do you see that? Well, what is, in this case, if you look at this diagram right here, what is sine of theta equal to? Y over r. So what does r equal? Oh, sorry. What does y equal? Y equals r sine theta, right? Similarly, what does cosine theta equal? X over r. So x is equal to cosine theta. The only common mistake there, sometimes people switch them and it results in something vaguely like the answer. Just be careful. So it's the bridge between the two. And we like this right here. Tangent of theta is y over x, and r is equal to x squared plus y squared. They do give you this warning. We chose tangent, but in general, theta does not equal tangent inverse of y over x. It's not possible to determine which quadrant theta is from the value of tangent alone. You just have to be careful about that. So choose a different trig function. Just choose sine or cosine. So we did one of these. We did one of those. Very nice. So this is what polar graph paper looks like, because all you care about is the distance from the origin and the angle measure, right? So in that case, P, what's that coordinate for P? If you wanted to write the coordinate for P, what would that be? 3 comma pi over 4. What happens if I gave you this one right here? What's that one going to be? 2 comma what? 5 pi over 4. Or many others. Yes, there's an infinite number of or plus n times 2 pi. Yes, it keeps on going around. Absolutely. Absolutely. So we already talked about A right now. What does r equal 1 look like in polar coordinates? It's a circle. Yay! How do you prove that though? So let's say you know that r is equal to 1. You know, what's that relationship you have in the triangle up here? You have this right triangle. What's the relationship between x, y, and r? What's the relationship? Yeah. You know that x squared plus y squared is equal to r squared. Well, you know from this that r squared is equal to 1 squared. So therefore, x squared plus y squared is equal to 1. Yay! So that's where it comes from. That's how you can go easily between the two. Converting between polar and Cartesian is usually relatively straightforward. Sometimes, though, it's kind of like the word clearly. You'll look at it and just be like, oh, it's obviously that. Sometimes you look at it and you'll be like, okay, wait for it. Wait for it. It's like those pictures you have to stare at until all of a sudden you see the sailboat. Like, just, there aren't that many things you can... Do you know what I'm talking about? The dot pictures? Oh, no one has seen the movie Mallrats, Kevin Smith's second movie? Really? Really? Yeah, you know the dot pictures? Like,
yeah, it shows like one, there's also one like it's a base for it.
Yeah, and you look at it until like the picture resolves, like it's not readily apparent. Anyway, who knows? Okay, so what about if we start changing the function? So it's the way you write polar functions is r in terms of theta, r in terms of theta. So theoretically, if I gave you those and you did not have a calculator, what could you construct if you wanted to make a picture of what these looked like? What could you construct? You could make a what? You could make a table. You could make a table. Now here's the thing about making these tables. While it is possible to choose trig values that are easy to plug in, common outputs to trig functions are things like root 2 over 2, 3 over 2, 3 root 2 over 2, things like that. Do you know the really clean decimal equivalents to those things? Not really. And is it really important to know what the curvature looks like and to graph these really accurately? Yes. What I'm saying is graphing polar by hand is going to be limited to relatively straightforward ones, or ones where you're given a really big hint. These right here, are these really annoying to have to do by hand, like super annoying? I think so. So what do you usually use when you're given things like that? Calculator. Graph both of those right now on your calculator. Lauren noticed I asked, like, how do you know which one is which? You might try to count the petals and things, but look how far out it goes. You have 4 cosine theta. That's going to have to go a distance of 4 at some point away from the origin. And the blue one for r equals 3 sine theta, that's going to have to go a distance of 3. What does the 2 and 3 theta do to the shape of the graph? So it says sine 2 theta. Let's say I did graph to 3 sine theta. What does it do to the shape of the graph? Yeah, so this is a really fun thing to play around with. Change the coefficients in front of theta and see what happens. It's kind of cool. Let's go. More petals, yes. I want someone to explain this to me right here. So this is the crux. This is the core of the next little thing we have to know about polar land. Area of shaded sector is 1/2 r squared theta. My question to you is, where does that come from? There, I like that idea. So what's the area of the circle equal to? The area of a circle is? I like that. Nice. But theta is less than the full circle, correct? Theta is less than the full circle. So how much of the circle, how would you figure out how much of the circle you have if you have that theta? Let's say you're in radians. Theta over what? 2 pi times what? Pi r squared. So this is the percentage of, that's the part of the area you want, and then that is the actual area. So when you cancel this, when you cross all these things out, what happens? Pi goes away, and what are you left with? 1/2 r squared theta. Is everybody with me so far? This represents the portion of the circle. What percentage in from 0 to 1? What decimal part of the circle? And this represents the area of the circle. Yes, Matt?
Is it a coincidence?
Of shapes traced out by polar functions. So usually, what do we have? We started off your integral land. You were finding areas under curves, right? You were finding like this area right there, the area under the curve. The ground, what's the ground? What's the ground equivalent? What's the x-axis equivalent in polar land? The origin. Everything is mapped back to the origin. So when you break this apart into an infinite number of pieces, we're not breaking it apart into rectangles, we're breaking it apart into sectors, slices, sectors. And those sectors look a lot like those. They are actually those. So is this radius the same as this radius? Are they, as you get them really close together, do they get really, really close together? Yeah. So when you take it as a limit, which you're not going to have to do because we have the fundamental theorem of calculus and we now just integrate. When you integrate an infinite number of these, glue them together, you end up with the actual area of the polar shape. And it's area because it's usually closed in, but you can think of it as area under. So remember, this right here, that's your x-axis showing everything under the function. The equivalent of underneath, down is always towards the origin. Down is always towards the origin. So what kind of integrals are we looking at? We're looking at this right here. For a curve r equals f theta, with f theta greater than or equal to 0, the area is given by 1/2 the integral from alpha to beta of f of the function squared d theta. So this right here is r. That's r right there. Do you understand where the 1/2 comes from? The equation, right? But what are we missing here? This equation is 1/2 r squared theta. Where's the theta right here? The d theta. It's an infinitesimally small slice of theta. It's an infinitesimally small slice of theta. Alpha and beta. What are alpha and beta equal to? What are they? I know the area of this shape right here. If I want to know the area of this shape right here, knowing the limits of integration going from a to b is just finding the x values for the starting and end points. That's it. Just starting the x values from the starting to the end points. It's not as straightforward. So for example, here is the graph of one of the functions we graphed before. R equals 3 sine 2 theta. So if we were to write the integral without the alpha and beta values, you would have the integral 1/2. And what goes right here? 3 sine 2 theta. What? Squared d theta. What's missing? The limits of integration. Now don't say it out loud. See if you can figure out the limits of integration on your own. Do that right now. See if you can figure out the limits of integration on your own. What's the starting and end? And we are just trying to come up with the area of that one petal. 0. I like this. You said 0 to pi over 2. I very much like that. How did you get that? How did you get that, Lauren?
Well, the theta is the angle measure, so.
So like if you're at this point right here, where do you go next? Where does this part, when you're tracing this function out, where does it go? It goes like this, right? So what's the angle measure at that origin point? 0. That is the angle measure. So if you go all the way around here, if we go all the way around, what's the angle measure once you come straight down? 90 degrees, which is pi over 2. The trick is, you have to be very careful about this, know how it's being traced out. Sometimes it's, like you want it to just do this, and it does do that, right? Here's the real question. Where does it go next, by the way? Down into the, it goes down into the right, correct? Doesn't it, does it do this? Or does it go like this? That's my question. So that all I want, the only point I want to make right now is don't assume anything about the path. Do you understand what I'm saying, everybody? So if you do this, hey, we've set up the integral. Let's just take solace in the fact that we've set up the integral. At this point, what might you want to be able to do once you've set up the integral? What would be nice to be able to do? Yes. Now, you've solved things like this before. If you had to do this by hand, anybody remember what method you have to use to integrate sine squared? At some point, you probably are going to use that. Yeah, but if you do 1 minus cosine squared, you're still stuck with integrating cosine squared. So the question is, do you remember how to integrate cosine squared or sine squared? Do you remember what method you have to use? It's parts, yeah. You have to use parts. You have to use parts. Do this for me now on your calculator, though. Tell me what it comes out to be. Theta. And you can write y entirely in terms of theta. You're able to do that. And if you have that, you can write dy dx as dy d theta over dx d theta. What kinds of questions do you think we're going to do with dy dx given a polar equation? Find what? Might find tangent lines. Tangent lines, for example. Yes, go ahead. Correct. Dy dx would be the Cartesian slope. That is correct. So to find the slope of the curve, we use the formula. Hey, what is this not dissimilar from? What's that very similar to? Parametrics. Right. We had y and x in terms of t. Now we have y and x in terms of theta. All we literally did right there was instead of t, we write theta. Nice. So do this for me right now. Using that formula, find me the slope of the curve. If I can get that off there. It's just really not. It just wants to keep that there. Do this one right here. Try that. If we want to do this, you know that x is equal to r something and y is equal to r something. What is it? What's x equal to? R cosine theta. And what does y equal? R sine theta. But over here, what do we know r is equal to? 3 sine 2 theta. So x in terms of theta is equal to 3 sine of 2 theta times cosine theta. And y in terms of theta is going to be 3 sine of 2 theta times what? Sine theta. So what do you need to do in order to find dy dx? We need to know what x prime of theta is, correct? What do you need to use? So 3 times the derivative of the first. What's the derivative of sine? So 2 cosine 2 theta, the derivative of the first times the second, plus the first. What's the derivative of cosine? Since we minus this, right? Is that good? Nice. So then what do we have to do over here? We can bring this over if we want, right? Move it over. So what's y prime of theta going to be? 3 times 2 theta sine theta, derivative of first times the second plus the first times the derivative of the second. How am I doing so far? So now could we write a statement for dy dx? Yep. So this right here, the general statement, this goes in the denominator, right? And what do we plug on the top? This thing right here. Is it nice that you can just paste stuff and not be able to drag it? There we go. So this right here is dy dx, right? Now at this point, if you want to know, we're trying to find dy dx when what? Theta is equal to pi over 3. Now, might we want to investigate trying to simplify some of this if possible before we plug things in? I mean, I would. I mean, what's one thing that definitely cancels out? Yay, 3's are gone. Nice. Now, at this point, is there anything? Did anybody factor this? Does factoring do anything for us on this one? Yeah, there's not really enough commonality. It's really close, right? Because you're like, oh, there's 2 things. Well, it's cosine 2 theta and sine 2 theta. It's sine theta and cosine of theta. So is there anything really we can factor out of this? Not really. So what do you just have to do at this point? Plug in pi over 3. You just have to plug it in. Exactly. So I'm going to stop here. You guys can figure it out. But do you understand the process? That's what I want you to understand at this point. Got it? Process good? Okay, stand up. Parametric, polar, and vector functions. We might have to spend a little more time with vectors, considering what I saw on the test. The most common half point I had to take off was kids doing way more work than they needed to. Applications of integrals. Oh, L'Hopital's rule. We talked about that. That's really fun. You love L'Hopital's rule, don't you? It's a really good time. Lots of antiderivatives. There's a huge block of text right here. We're about to get to improper integrals. We've seen them a little bit. Wow, logistic differential equations is coming up. Oh, we've talked about series, harmonic, alternating, all sorts of, Taylor series. Remember that fun land of fun? Fun land of fun? It's a good time. Okay, so what I'd like you to do, in addition to the homework that's listed tonight, which is some questions from 8.3, I'd also really like you to look at this document right here and make note of anything that we haven't covered at all or that you think we need to spend significantly more time on. There's definitely some stuff we haven't gotten to yet in depth, like improper integrals in depth, logistic differential equations in depth. But there's a lot of stuff on here, and I have to mesh it with things you did last year, with what we need to do this year, and then once we tee that up, we'll review it come March and April before the May exam. But I wanted you to add that to your homework. Brief discussion here. So this is arc length, right? Can someone tell me why it might be pretty brutal to use this formula? Why might it be pretty brutal to find arc length in polar land, unfortunately? Yeah. What? A, they overlap. You have to be really careful that you don't overcalculate. But can you tell me algebraically what's kind of annoying? The what? Yeah, the dx d theta and dy d theta. We already did that, right? Take a look at that. There's x prime and there's y prime, right? What do you then have to do to do the... You then have to square it. Ew! Not cool, Mr. Seamon. So, by hand, I am not going to throw something like this at you, for example. It's kind of nasty. This would be something that would be calculator aided. Otherwise, it would just be really hard. We're all set. Get out of here.